Okay, so then we have our again our conduction system. So how do they trigger the rest of the conduction system? Well, now we have to zoom in. Now we're looking not only at the conduction system, we're looking at the cells itself. And this is what makes cardiac muscle special compared to the other types of muscle, is this thing we call intercalated discs. Now I have to borrow one of the figures from the Martini version. So what we have here with this intercalated disc all around here, we have something called gap junctions. So gap junctions, when they're open, or actually that might be a little advanced, they can open and close, but if they're open, they're like tiny little pores that actually connect the cytoplasm of connected cells. So the cool thing is that these two, so we would have one cardiac muscle cell here and one cardiac muscle cell here. So the cool thing is it connects the cytoplasm. It connects water, ions, small solutes like glucose. Yeah, so the thing is that if you have ions, they can cross from one side to the other. So that's the cool thing about these intercalated discs. They're more than just a histological structure. They're actually very important connections between cardiac muscle cells. Now, what happens if you have a rush of sodium or any ion into one of these cells? Well, if these gap junctions are open, these ions can flow into neighboring cells. And this is what happens with pacemaker cells and conducting fibers. When these pacemaker cells have the rush of sodium and calcium from their action potentials, they can actually pass on the sodium and calcium to neighboring cells. And so this is one way that you can pass on an action potential from a pacemaker cell to those conducting cells and fibers we saw in that conduction system. So yeah, this is how you're able to do that, because of these gap junctions that allow ions to flow from one heart cell to another heart cell. Now hopefully I'll get to this toward the end. I might run slightly over time. So this is like zooming out. You have a rush of ions into one cell, but due to gap junctions, and this is why I borrowed the Martini version, is that there's little gap junctions, little pores in these intercalated discs. If you have a rush of one ion into one of these cardiac muscle cells, these ions can be passed on to neighboring cells. So that's the cool thing about the heart. A change in membrane potential in one cell can affect its neighboring cells. So this is why the heart is so cool. Alright, so does that mean the heart is completely independent of the brain? It's not completely independent. So it can beat without the brain, but so that's why if someone is brain dead, they can still have a heartbeat. But that doesn't mean the heart is completely independent in a healthy individual. So the cool thing is that your brain can even though your heart has its own system, your brain can kind of dial up the pace of the heart pacemaker cells or can slow it down. So your brain can adjust the activity. So it doesn't mean like your heart is not listening to your brain at all. It's probably listening to your brain right now. But again, depending on the situation, does it want to speed up your heart rate? Does it want to slow down your heart rate? So even though I showed that cool thing with the heart being without the brain, yes. And yeah, someone said it. A sympathetic and parasympathetic system, I think it's near the end of the chapter. So sympathetic, remember your heart starts beating faster and starts pounding harder. Sympathetic is going to dial up the speed, cause these pacemaker cells to actually start reaching the threshold faster. But parasympathetic, when you're relaxed, it's going to delay that pacemaker cell so that you can relax a bit and slow down your heart rhythm. Okay, I'm going to try to go over ventricular cardiomyocytes real quick. Okay, so this is where it gets really complex. Again, if you don't get it today, I don't blame you, because, and starting with PHYL 142, there is more than one type of action potential in the heart. So the thing is that you have the pacemaker cell action potentials, which we just learned about, and there are SA node and AV node potentials. I think they're slightly different. I don't expect you to know the difference. And there's also different action potentials. I mean, they're actually very similar they're kind of interesting. They're almost like they have prepotentials, but the overall shape is more like a ventricular potential. It's kind of in between. So you have atrial action potentials. They're actually, notice that they do, the common thing in action potentials, the cell starts in the negative and jumps towards the positive and goes back toward the negative. But the overall shape is different. And ventricular action potentials, they're also different from pacemaker potentials. So this is what I want you to know for this class, is that we're atrial and ventricle. I'm going to cover ventricular action potentials because atrial is very similar in terms of the overall mechanics. It's just like a slightly different timing between these phases.